Hello guys, so today I want to show you the proofs of the first and second theorems of calculus. So the first theorem says that the derivative of an integral from a to b of ft dt will be, so the integral with respect to x of the integral from a to x, actually, because x is our variable, the integral derived will be f of x. And now let's first visualize how our function and how our integral looks like. So let's say we have a function y equals f of t, and we have two constants, a and b, and the requirement for f of x or f of t is that it has to be continuous on intervals in the interval ab. Actually, this is a requirement for derivation, so we are actually not deriving f of t, but yeah, maybe I'm not exactly sure about this thing, but it's not that important. So let's take in our interval a variable x, and we will denote as the area under the function f of t between a and x will be the integral from a to x of ft dt. And this means that we take infinitely a sum of areas, infinite amount of areas from infinite rectangles that have the width dx, and they will have respective heights. This height is f of a, for example. The next one is f of a plus dx, and so on until this one is f of x minus dx, I suppose. So when we add all these areas, we will get our integral. And now let's think what happens when we try to derive it. So we have our integral derived with respect to our variable x, and we have to write in our numerator what is the change in our function integral when there is a small change in x, and this small change in x is dx. So we have the integral from a to x plus dx of ft dt, where we have to subtract our initial integral, divided by dx. Now we already said that this is our area, which is the integral from a to x. And if we try to visualize this integral, it will be our initial integral that has one more rectangle added to the sum, one more rectangle area, and this is also dx, and this height is f of x. So the whole integral will be this whole thingy. So now when we subtract the initial integral, we will be left with only integral from x to x plus dx, ft dt, divided by dx. And what did we say that this is? So this sum will only have one element, and this element will be actually this area. And what is this area approximated to? This is nothing else but the width of this rectangle, the length, sorry, of this rectangle, which it is f of x, because this is in the point x we are looking at. So this is f of x times our width, which is dx always. And because we have in our denominator also dx, these two will get cancelled out, and we will be left with f of x. So this is a nice proof. It shows more the intuition, how to think about deriving an integral. Now let's look at the next proof. The second theorem says that an integral from a to b ft dt will be f of b minus f of a, where f of x is no one else but integral from a constant c to x ft dt. So in other words, f is the antiderivative of small f. Big F is the antiderivative of small x, and that means when you derive it, you get to the small x. But we don't really use this right now. Let's again visualize our functions. We have our function y equals f of t. And let's put our constants c, a, and b. And let's look first at f of b. Using our formula, we get that big F of b is integral from c to b ft dt, which is integral from c to b, so that means the whole area, this one, is f of b. And f of a will be integral from c to a of f d dt. So this guy will be from c to a. Now it is very obvious when we subtract the bigger area when you subtract the smaller area from the big one, we will be left with this part. And this part is denoted as the integral from a to b ft dt. So this was really very simple, just using the integral formula and replacing it in the big f of b and big F of a. And my feeling is that this would work if we would even have minus infinity instead of c. It doesn't matter how big the area is. So if the areas were extended to minus infinity, if we subtract one from each other, they will cancel out anyway, because this part is common to the both integrals. So thank you for watching, and let me know if I explained it well enough. If not, I can make another video with more details. Thank you for watching. Bye.